All right, hello everyone. I am just setting up right now. It's been a bit. I've been out of town. I was in New York City, and then I'm sick. You might be able to tell from my voice. Hopefully not. Anyways, I am going to continue from where we left off. Now, I'm not at 100%, so if at any point I feel like I'm just turning this into a disaster stream, then I'll stop it, and then we'll have to continue next time. But hopefully, I am healthy enough to do a proper stream here. So let's see to that right now. I want to make sure everything's up and running. Let's see here. Okay, just need a second. Okay, so my speaker's working fine. And we are doing, this is 3.2. So the usual rules apply. We are doing the book of Proof, 3rd edition, Richard Hammock, and you can download the book in the video description, and it's free. Get the book. It's a great book. You know, that way you can follow along. I don't know the answers. I do the questions, and then I go and check to see what the answers are in the back of the book, so you can actually know before I do. Yeah, so feel free to do that. Okay, so now we are in 3.2, and again, I'm going to read through the chapter, and then I'm going to work through the equations, and anything that's relevant, I will try to write on here, but feel free to read along in the book. All right, so the multiplication principle. Many practical problems involve counting the number of possible lists that satisfy some condition or property. For example, suppose you make a list of length 3 having the property that the first entry must be an element of the set A, B, and C. So let's just write this down. Okay, so we have sets here. So we're going to use set notation. A, B, C. Okay, the second entry must be from here. 5 and 7. And the third one has to be A and X. Thus, A5A and B5A. So here's examples. Okay, so we take 1 of 1, we take 1 of 2, and 1 of 3. And here we're going to take 2 of 1, 1 of 2, and 1 of 3. Okay. Now, how many lists are there altogether? To answer this question, imagine making a list by selecting the first entry, then the second entry, and finally the third. This is described in figure 3.1. That's what we did last time. The choices for the first entry are A, B, or C, and the left of the diagram branches out to 3 choices. For each choice, once the choice is made, there are 2 choices, 5 or 7 for the second entry. And when this is described graphically by 2 branches from each of the entry, and this continues with the third entry, which is A or X. So basically we have, so if we look at it, how many items are in here? So let's just say this. What's the cardinality of the set? And that is 3. What's the cardinality of this set? That's 2. What's the cardinality of this set? It's 2. So in order to find out what are all the possible mixtures without any preconditions, we just multiply by the number of variables. So that's going to be 12. All right? Okay. 12 possible ways, again, without any preconditions, such as you could only use the letter A once, for example, or something like that. Anyway, here we go. In the above example, yeah, this is called the multiplication principle. We will do one more example before stating this important idea. Let's see here. So here we go. Consider making a list of length 4 with the 4 letters. So let's do another one. Okay, so then now we have our list. A, B, C, D. Okay, fix this bracket. I can't salvage that. You know you're good at proofs when you can write decent brackets. So I'm not quite there yet. All right, so then we have A, B, C, or D. Now, you're not allowed to repeat a letter. So basically, this list, you're not allowed to have a repeated letter. For example, A, B, C, D, and C, A, B, D are allowed, but A, B, C, and C, A, B, C are not allowed. So in other words, you have, you're making a list length of 4 from the 4 letters. How many ways can you combine the 4 different ones? Now, if you're allowed to repeat them, and you're making a list length of 4, you would take 4 times 4 times 4 times 4. So that would be the way to get that. And that would be 64. But in this case, if we're not allowed to repeat, we just drop 1 letter. So it's going to be 4 variables for the first one, and then we're going to say times 3 variables for the second chance, 2 variables for the third chance, and 1 variable. So that gives us 24. Okay. That means there's no repetition allowed, and yeah, that's how that works. By the way, if you feel at any time that I'm ever going fast or anything, feel free to just like look through the book. They have great diagrams. I mean, I'm not going to spend 2 hours drawing out the diagrams. When just download the book and look at it. It'll look nicer in the book anyway. And they list all 24 variables here if you want to see it, and they have a nice branching diagram. Anyways, here we go. These trees show that the number of lists constructible by some specified process equals the product of the numbers of choices for each list entry. This summarizes this kind of reasoning as an important fact. Fact 3.1, multiplication principle. Suppose in making a list of length n, there are a sub 1 possible choices for the first entry, a sub 2 possible choices for the second entry, a sub 3 possible choices for the third entry, and so on. A total number of different lists that can be made is a product of a sub 1. So basically, if you have a list of length n, and then, so a sub 1, sub 2, and then a sub 2, a sub 3. So to get the full thing, it's going to be a sub 1 times a sub 2 times a sub 3, and all the way to a sub n, basically. And that's just what we did there. Like I said, if there is no precondition, just multiply it by the number of possibilities for each entry. If there is a condition to where there's no repetition allowed, then you're dropping 1 per iteration. In using the multiplication principle, you do not need to draw a tree with the branches. Multiply the numbers. Yeah, that's what I was saying. Example, a standard license plate consists of 3 letters followed by 4 numbers. JRB-4412 or MMX8901 are 2 standard license plates. How many different standard license plates are possible? Well, a license plate that corresponds to a length of 7 lists. So we need to count how many such lists are possible. And then in this case, so if we say a license plate, let's just do this real quick here. So we have, let's A, B, C, dash 1, 2, 3, 4. How many possibilities? A sub 1 is going to be 26. A sub 2 is going to be 26. Because you can have A, for example. A sub 3 is 26. And then numbers, they can be 1 through 0. So you can get 10. A sub 4 is 10. A sub 5 is 10. A sub 6 is 10, a sub 7 is 10. Now, just to be clear, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7. Okay? The subscript is just a way of counting it. We use subscript to give it a number placement, and that way it's not confused with like powers or anything like that. Anyway, so then we just have to multiply all that out. Let's do that with a calculator. So all we got to do is multiply 26 to the power, take it to the root 3, and then add 4 zeros, basically. Or multiply 26 times 26 times 26. Okay, and then times 10 times 10 times 10 times 10. So yeah, basically it's going to be, here's the number. 17.5 million, I think. Yeah. 0, 0, 0, 0. 4 zeros. Sorry, 175 million and 760,000. There we go. All right, yeah, so that's all the possible ways to have a license plate number. It's pretty wild. Okay. And another example, in ordering a cafe latte, you have a choice of whole, skim, or soy milk, small, medium, or large, and either 1 or 2 shots of espressos. How many choices? So let's count. We have the first one is whole, skim, or soy. That's 3. The second choice is going to be small, medium, or large. That's 3. And the last one is going to be 1 or 2 shots of espresso. So 3 times 3 is 9, times 2 is 18. There are 2 types of list counting problems. On one hand, there are situations in which list entries are repeated as in license plates or telephone numbers. The sequence CCX-4144 is perfectly valid license plate in which the symbols C and 4 appear more than once. On the other hand, as in milk-sized shots, list from example 3.2, we say repetition is allowed in the first type of the list, and repetition is not allowed in the second type. Because, you answer the question. You wouldn't want 2 types of milk. I mean, I suppose someone could, but it would be weird. Anyway, okay, we will call this list in which repetition is not allowed a non-repetitive list. The next example illustrates the difference. Okay. All right. Let's open this up. Consider lists of length 4 made with the symbols A, B, C, D, E, F, G. How many lists are possible if repetition are allowed? So we have let's see here, symbols. And then, let's see here. So we're going to say A, list, length 4. Okay, and we're going to say repetition allowed. Let's see here. Okay, so we have length 4, and then we have 1, 2, 3, 4, 5, 6, 7. 7, right? And repetition's allowed, so that's going to be 7 times 7 times 7 times 7, okay? So that should be 2401. 2401. So we took each of those, and then we could stick it in there. Each time we don't drop anything because repetition is allowed. We could have A, and we could have G. So that's fine. How many such lists are possible if repetition is not allowed? Okay. So in this case, if repetition is not allowed, that means, for instance, on the first choice, Okay, so on the first choice, we have 7. On the next one, we're going to say we can have all but one symbol. We can't have, for instance, A. We could say that we can't have AA. So we were going to drop one symbol. So in other words, we can have, first one can be A through G, and the second one can be any number, but it cannot be, it could be any combination, I should say, but it can end up with having repetition of one of the numbers. So that's how we do that. We drop the 1, so that's 6. Next one, we're going to drop one more, 5. I have 4 possibilities. By the way, a lot of the stuff that I'm going through, but it's 840. Yeah. So like a lot of the stuff, you might be like, hey, wait a minute. Is that really how it works? You could sit down and take a smaller set and work it out. Like take sets of 4 or write out your letters and just to really convince yourself. But yeah, that's how it works. And some of the stuff, a lot of it might be going over your head. That's fine. The important part is to just keep writing. And by writing, I mean you have to not just listen to anything anyone says. Like I myself know from lectures that a lot of them would go over my head, and this is a class I'm preparing to retake. So this is why I do this. By studying and solving it for myself, I am preparing myself, and it actually, the retention is so much better when you have to work through it, especially if you try to present it to someone else, because you have to work it out in your head in a way that will make you understand it. But really wrestling with math is the only real way to get it. You have to put pen to paper. You have to wrestle with it. And it's not something that's intuitive. You have to work your way through it. And lectures or audio podcasts or anything alone will never do it. You have to write it down and do it. Anyway, let's keep rolling. C. How many are there if repetition is not allowed and the list has an E? A minute here. Okay, so basically, this is an interesting one. Okay, how many are there if repetition is not allowed and the list has an E? Okay, so right now this is still the explainers here. So by saying that we have E, here we go. I'm going to read part C here, because this is something that the first 2 ones, they've already taught us. Now they're going to teach us how to do it when they already put a precondition in there. Okay, I'm just going to write this down here. Okay. Reading C here, and we're on page 70. We are asked to count the length of list 4 lists in which repetition is not allowed and the symbol E must appear somewhere in the list. Thus, E occurs once and only once in each list. Let us divide these lists into 4 categories depending on whether E occurs in first, second, or fourth entry. Third or fourth entry. These types of lists are basically we have E in the first, and then we have 6, 5, 4. E in the second, we have 6 options for the first because there's no repetition allowed, 5 in the first. So essentially, what we get is that by E taking up a slot, our 4-letter list, so we have blah, dot, 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 right? Doesn't matter where you stick the E. We're just going to say E can go anywhere. Where effectively we're scratching one option, right? And that scratches the E. So now we have 3 options, and we have no repetition allowed. So now we have 6 for the first, times 5 for the second, times 4. Okay, so that's going to be here. 30 times 4 is going to be 120. So that's 120. Is the number of possibilities. So that's a easy way to think about it. E locks in a spot. Now, because it doesn't require us where they order what happens, it's a little easier because in that case, regardless of where the E happens, it's still going to be 6 options for whatever slot. And if E, for example, let's do this for a minute. All right. I'm just going to redo it here. If E was right here, that's going to be 6, 5, 4 options. If E was right here, it would be 6, 5, 4 options, like that. And I mean, technically, you can go 4, 5. I mean, I wouldn't say 4, 5, 6, but essentially, whichever order you want to go in, every time you populate a letter, it reduces the amount of options for the next spot you want to populate a letter by 1, because there's no repetition allowed. But yeah, so then here we go. Now, except it's not done yet. Let me see here. Now, okay, E. However, as shown before, there's also for E in the second. So, now what we have is, but because we have E here, so that equals 120, and then we have 1, 2, 3, 4, 6, 5, 4, and then we have 6E, 5, 4, that equals to 120. This is a different type, see? 6, 5, E4, and then we're going to say, which equals to 120, and then we're going to say 6, 5, 4, and E. The reason why I'm starting with 6 and not 7 is because of that E, we can't have that repetition. So automatically that takes out the repetition. So that, now here's what's different about this set. Because these are different types of set, it's not just the 120, it's the 120, and it's all of those 120, so it's times 4. Okay, so that's going to be 480. Okay. And so these are very important things. Yeah, when we're going to get to the questions, we're going to have to double back and review these while answering the questions. All right, D. Let's see, what is the question for D? How many are there if repetition is allowed and the list has an E? So now repetition allowed. By the way, these ideas, they're very powerful, and as the structure of it, it's very good to just like to understand it and just like work through it enough to where even if you aren't convinced by it, at least you can pull it out and say, okay, if someone says to you, how many possible ways you can arrange your work week schedule, you know, something like that, then you can just quickly do a back of the envelope calculation and know. So yeah, these formulas, they're very important. So anyway, I wouldn't even call it a formula, but essentially this algorithm, you can think of it that way. All right. Anyway, so what we have here has an E. So in this case, we need 4-letter lists and repetitions allowed and must have an E. So here's our strategy. Let's see here. By part A of this exercise, we know that there's 2401 lists where repetitions allowed. That's not the question because many of those lists do not contain an E. So we want all possible options. Repetition allowed is 2401 because that's going to be 7 times 7 times 7 times 7. List has an E. That's going to be... Okay, so we have to figure out how many have an E. So in making a list that does not contain an E, we have 6 choices for each list entry. So we want to... Remember, it has to have an E, so we have to figure out how many lists do not have an E. So, basically, we have 6 choices for each entry because there's only one E in the list. So we have... Okay. Okay, so we have 6 times 6 times 6 times 6. All right, so then we have 1296. Okay, so now what we have is lists with no E, right? And then we have repetition allowed. So here's what we got. Okay, let's see if I want to. I'm trying to think if I can do like a Venn diagram to demonstrate this. No, it's just I'm overthinking this thing. Okay, so if we want lists that have no E but are in the repetition allowed, we have to take that out. So we have 2401 minus 1296. Which is 1105. Okay, so yeah, this is a little more involved. Still, it's not terrible. This idea is pretty straightforward. So a lot of these questions going forward, you just have to take your time to really think your way through it and make sure that you're just like not just jumping right into it, because it's easy to mess them up. But if you take the minute to really think it through and understand the process, it's not too bad. Before moving on from example 3.3, let's address an important point. Perhaps you wondered in part D could be solved in the same way as part C. Let's try doing it that way. We want to count list for lengths repetition allowed that contain at least one E. So basically, here's what we're doing here. The only difference is now there are now 7 choices in each slot because we're allowed to repeat 7 letters. Okay, we get a total. Okay, so okay, so you can't do it with that option where, okay, if you were to go like this, so we're going to say E and then a 777, that does not work. You actually get a bigger number. So, and yeah, you can't do that. It is easy to see where it went wrong. The lists EEAB is a type of 1 and type 2, so it can get counted as twice. Similarly, EECE is a type 1, 2, and 4, so it got counted 3 times. In fact, you can find many similar lists that were counted multiple times. In solving counting problems, we must always be careful to avoid this kind of double counting and triple counting or worse. Yeah, so that's something to really watch out for, is we want to make sure that we're not double counting our lists. Okay. The next section presents 2 new counting principles that codify the kind of thinking we used in parts C and D above. Combined with the multiplication principle, they solve complex counting problems in ways that avoid the pitfalls of double counting. But first, one more example of the multiplication principle highlights another pitfall to alert to. All right. So now we have a non-repetitive list of 5 to be made from the symbols A, B, C, D, E, F, G. Okay, so we have. Okay, A, B, C, D, E, F, G. All right. And the first entry, has to be B, C, or D. And that last entry, a vowel. So that's A, E. Okay. Okay, so we're going to have 5 boxes. Box, box, and box. Okay, so we have 5 boxes, and we have to figure out, so the first box, what options do we have? So it says B, C, or D, so we have 3 choices. You can choose 3 in the first one. And this is non-repetitive. Now, that leaves us so that we have, let's see here. And now in the second one, now remember, that's going to lock in 1. So that takes 1 off of our total number of 7. So that makes it 6 for the next one. So this one, we're going to have 5 options. We have 4 choices. And then, let's see here, make sure. But the last box, there is a problem. It's supposed to contain a vowel. But for all we know, we have already used it up, 1 or both vowels in the previous boxes. The multiplication principle breaks down because there's no way to tell how many choices there are for the last box. The correct way to solve this problem is to fill in the first and the last boxes that have restrictions first. Aha. That's what we got to do. Right, so then we have to do the restrictions first. We have 3 here. We have 2 here. Okay, so now these 2 are locked in. So now we're going to have our choices 7 minus 2. Because 1 and 1 get taken. 1 from last, 1 from first. So that makes us 5 options. And then we're going to have 4 options, 3 options. Okay. So then we're going to say it's going to be here by multiplication principle. 3, 5, 4, 3, 2. Okay. Okay. That's 360. All right. The new principles to be introduced in the next section are usually used in conjunction with the multiplication principle. So work a few exercises now to test your understanding of it. All right. Wow, that's pretty good. We've covered some good ground. Now we have to do the question and answer part. All right, that was fairly brisk, I must say. All right, let's see here. So yeah, usual rules apply. I am gonna do the odds. They have answers in the back. I don't know if I'm getting the correct answer or not until I check it. And I don't do the evens because I don't want to damage the integrity of the book as a teaching resource. Okay, so okay. All right. A. Okay. Sorry, I'm a little sick. 94. Okay. So we have 4 slots. 2, 3, 4. So then we're gonna say we have 1, 2, 3, 4, 5, 6. Always important to count, right? Like, you know, you can just like ballpark it and think, oh, it's really 7 or 5 letters. You might just like make a simple, stupid mistake like that. No, just pound out the letters. Make sure everything is counted up. There are 6 length 4 lists, 6 options for the first one. We're repeating it. 6 options for the next. 6 options, and guess how many for the last? 6. Look at that. Because repetition's allowed. All right. Let's see this. Okay, that's 1296. We're going to say 1296. I don't know if that's the correct answer, but I believe it is based on everything we've done so far. Okay. Okay, B. So we have length 4. Length 4. begin with T. Okay. So 2, 3, 4. So we're going to say T, and repetition is allowed. So we're going to say 6, 6, and 6. Okay. Yeah, so then basically when that is, we're just going to multiply those out. We'll go back and check how we did this. Right, yeah. So like we don't worry about T as a factor, or you can think of it as 1, I guess, but basically it's 6 times 6 times 6, 216. All right. How many length 4 lists are there that do not begin with T? I'm sorry. I am just being dyslexic. I'm not normally dyslexic, but I'm just like so ill right now that like I spent 19 hours of sleep, and 2 days ago, like last night I kind of slept okay, but the night before I was just like semi-conscious for like almost 24 hours. Anyway, I'm not complaining. I'm just saying why I'm writing all funky. Length 4 lists and do not begin with T. Okay. All right. Do not begin with T. So that how many options are there? Okay. So well, there's only 5 for the first one, and then everything else is going to be 6, 6, and 6. All right. Okay, that should be 1080. So that's 216 times 5. All right. Yeah, let's take a look. See what the book said. Okay, 1296 for the first, 216 for the second, 1080 for the third. Good. All right, so far so good. All right, 3. How many lists of length 3? Okay. Length 3, and then we have A, B, C, E, F. If repetitions allowed. How many lists of length 3 can be made? Okay. Same question as, I think, hang on a minute. Yeah, how many lists of length 3 can be made from the symbols? How many do we have? 1, 2, 3, 4, 5, 6. Again, there's another 6 variable option. A repetition allowed. Okay. Okay, so then we're going to say first one is 6, 6, 6. Okay. It's 216. Yeah, 216. All right. Now we're going to say B. Repetition is not allowed. Okay. So we just drop 1 per thing, per iteration or permutation. Okay. All right, so we're going to say 6, 5, 4. $120. And C. Repetition not allowed and the list must contain an A. Okay, so remember how we did that last time. So this is not allowed. plus must have A. All right, so there's 4 options right away, so let's just establish it. A blank 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 A blank 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 A blank 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 A, and we're going to add all those together. We're going to add them all together. So and then no repetition. So let me see here, make sure that. So because, I'm going to double check based on the previous example, but yeah, let's see here. So right, we can no longer do, right, because we can't have the repetition of A, so that means we have to start with 5, 4, and 3. Okay, we're going to say 5, 4, 3, 5, 4, 3, 5, 4, 3. Okay, and then we're just going to multiply those out. So that's 5, 4, and 3 is going to be 60 plus, I'm going to say each 60, 60, 60. Okay? It's going to be 240. 240. All right. That should be correct. We're going to find out in a minute. All right. Well, only one way to find out here. Let's take a look. All right. Okay, repetitions allowed. First one's 216. Repetition is not allowed. Answer is 6 plus 4 is 120. Repetition C is not allowed unless must contain A. Repetition is not allowed unless must contain A. It's saying 60, which I got 60. Why did I do it 4 times? Hang on. Oh. Okay, hold up. That's where I messed up. Yeah, it's a list of length 3. I made a list of length 4. So it was correct, but let me fix this. It was also incorrect. Incorrect because I did it wrong. Kind of blazed through that. I answered my own question correctly, but not the book. So, and that's a common thing that, if you go too quickly, you can mess up. Check your work. Let's do this correctly. So we're going to say, so the first 2 are correct. The third one was wrong. So we're going to fix this real quick. A. Okay. So we have 3 A's. So now we drop the A. We have 5, 4, 5, 4, 5, 4. I'm going to add it. 20 plus 20 plus 20. You get 60. Okay, that's correct. All right. And then D, repetition is allowed and a list must contain the letter A. So in the last one, plus A. Okay, so then we have here, let's kind of move this thing down a little bit. Okay, that's good, I think. Yeah, okay, a little lower. Okay, good. So we're going to say, oh, right. Well, it's same thing. We're going to make A. The difference now is we can have multiple. We could have the A's as well. So we're going to say 6. And so repetition is allowed. So we have our full range. The only difference is we're locking out one of them. And we're going to say 6 and 6 and 6 and 6, 6 and 6. I think that's how this should go. Let me see here. Let's see, 36 plus 36 plus. I don't know if this is going to be correct, but we're going to find out in a minute. That's what I think it means. 108. Okay. Oh, okay. No, not like that. So basically what I did wrong was repetitions allowed and the list must contain the letter A. So that was done incorrectly. I'm going to fix this. It just takes a bit of getting used to how all these lists work and stuff. So the problem with the way I did it, and this is how they had in the previous, when we were learning it, is that I double counted and my list was too high. So repetitions allowed, right? So we can have AAA, for example, right? So let's just say all possible lists. That's 6 times 6 times 6. Okay? So that's going to be... That's 216. Okay, then we're going to say all no A. Times 5 times 5. It's 125. And then we subtract the 2. Okay, and that's 91. That's the correct answer. So anyway, this is gonna take some getting used to. Just all the ways repetitions allowed, not allowed. It just kind of like you have to remember the rules. So let's just look it over again. If repetitions allowed, you're gonna you have your list length, which is 6, for example. You're gonna go full length times full length times full length. Okay, so that's pretty straightforward. Repetitions not allowed, you're dropping 1. You start with the number, you drop 1, and then drop subsequent 1 for each one. That's fairly straightforward. Okay, no repetition must contain the character A in this case. So this was also kind of straightforward. We just have to trace it through it and then work around it. So this kind of a grid works. That's with no repetitions. So remember, no repetitions and must have a character or characters. We could lock in the characters and then no repetition. Now, repetition allowed plus having a character, you have to take all the possibles and then all where A does not appear and then subtract them all like this. So some of it might not be intuitive. That's okay. We just have to keep working our way through it. It'll click eventually. All right. Okay. 5. This problem involves 8-digit binary strings. That's just 1, 0, 0, blah, blah. 8-digit numbers compose zeros and ones. How many such strings are there? Okay. Okay, so we have 8. So then there's 8 places, so it's going to be 2 to the power of 8. Five, 6, 7, 8. Okay, that should be 256. All right. Binary. So it's going to be 0, 1. And then, so then we have, how many strings end in 0? Okay. So then, so let's just think about this for a minute here. So we're going to say the last one is 0. And we're going to say 2, 2, 2, 2, 2, 2. So that's all the possible strings. Again, I don't know if I'm going to get this answer right or wrong. I'm just working my way through it. If I get it wrong, I'm going to come back and fix it. It should be 128, just one down. Yeah. Let's see. So this is A. This is B. All right. How many strings have ones for their second and fourth digits? Okay. Let's try this. All right. Right. So we have, for C, we have ones for their second and fourth digits. So then we're going to say 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4. Okay. Okay. That should be 64. And D. Again, bear with me. I'm solving this, so I don't know if I'm going to get it right or wrong. If I get it wrong, though, I'll work through it and fix it. How many strings have ones for their second or fourth digits? Okay, so then, let's see here. So then we have their only second or only fourth. I'm guessing this means, I wonder if this is an exclusive OR or not. Can it be one or the other or both? That's a trick, isn't it? Is it an exclusive OR or not? I'm guessing it's both in this case. Like one or the other or both. Should make sense. I would say we have to figure out how many have the one digit, and then we add it with the other. So let's say 1, 2, 3, 4, 5, 6, 7, 8. We're going to say 1, and then we're going to say 1, 2, 3, 4, 5, 6, 7, 8. And then, well, if you did it that way, that would give us the same number, though. And I know it's not the same number because, for instance, all zeros is a valid solution to this, and that would be... So let me think about this for a minute. Fourth. I guess the other way to solve it would be reverse it. How many actually have zeros at both of them? If we have zeros at both of them, and we can subtract it from all possible possibilities, and it would get us the same result, I think. So yeah, like if... So that's like doing a not. our logic. So what if we did that instead? What if you went like this? We're going to find out 1, 2, 3, 4, 5, 6, 7, 8. We're going to say how many have zeros in the second and in the fourth, right? So then if we did that, it should be 64. And then from the total possible, that's 256 minus 64. 56 minus 64 is 192. So I don't know if I'm right on this or not, and I feel like I'm cheating a little bit because I took the or and I flipped it and got the negative and got the and. But then again, they have been teaching this in logic, so if I get this right, I'm feeling a little cheeky about it, but I don't know. Let's find out. I'm probably going to get this wrong. All right. Let's see here. Okay. All right. Let's see here. 5 is 256. Let's see. B is 128. C is 64. D. By the multiplication principle, there are 2 to the power 664 strings of each type. So there are 364. There's 192 8-digit binary strings whose second and fourth strings are ones. So yes, I got it in a roundabout way, which again is not wrong. I simply inverted it, just like doing the not. It's a logic thing. So basically, yeah, this is what they teach us logic for. Sometimes it's easier to get an inverse and then come back in and take that out and get the result you want. But let's see how they did it exactly. How many such strings are such there are second or fourth ones? The strings can be divided into 3 types. Type 1 consists of those strings of 1 in the first and 0 in the second. Type 2 consists of 0 in the first, 1 in the second. Type 3 consists of 1 and 1. By the multiplication principle, there are 2 to the 664 strings of each type. So here's what they did. So like I said, I am a little cheeky about the way I did it. So here's what they did. They did this. So they did the first type, 1 and 0, and then we're going to have asterisk, asterisk, asterisk. Actually, forget about the asterisks. We're just going to use the 2s like I've been doing. That's fine. It's still to the power of 2s, right? And the second type is going to be right here. So this is going to be here. 0, 1. And the third type, these are all valid options, basically. They're counting up the valid options. And what I did was I counted up only the invalid options. See how they have to do 3 sets? And I'm like, you can do that, but you could also just count up the invalids and subtract them out. And because this is base 2, it was simple enough. But this is why you have to also know how to do it the right way, because sometimes it's not that simple to take out the invalids. So each of this is going to be 64 plus 64 plus 64, which is also 192. Okay, so like I said, I took out the invalids from all possibles. They counted up all the valids. So yeah, it's the same thing. All right. All right. 7. The problem concerns 4-letter codes made of the letters A, B, C, D through Z. Okay. All right. A through Z. Okay. Okay. So we're going to say 26 times, a minute, let's do it this way. 4 letter codes, 1, 2. There are 26 letters, so we're going to say 26, 26, 26, and 26. So this is a lot like the license plate, only simpler. So far, 26, 26. There we go. At least, again, I won't know, of course, till I check the answer, but it seems pretty straightforward so far. How many such codes can be made with no 2 consecutive letters the same? No 2 consecutive letters the same. Oh, that's where the tricky one is, huh? I have to think about that. I think we can do this. Let me see here. No 2 consecutive letters the same. Well, we only have 4 slots, so we're going to say, let's just brainstorm our way through this, okay? So we can have 26 in the first one. Well, in that case, we can have 25 options for the next. So I think, and then I would think that we can do, we can't do 25 in the next one because, actually maybe we could, because it frees up the first letter. Let's try this on a simpler version. So let's just say, what if our letter code was ABC? A, B, C, D. So we're just going to try a simplified, a toy model, so to speak, here. We're going to say, first one we're going to say 4. Let's see, the second one can be 3. What can be for C, though? So we can have 3, probably. Because we can have A, B, C, D, and then we're going to say B, C, D, and then this one, we're going to say A, C, D. A, C, D, because if this is B, then we can say A, C, and D. So that's not consecutive anymore. So that's 3. And then we're going to say, for the last one, again, we should be able to do, I would think, 3 because they're not consecutive. If this is C, we have A, B, and D. All right. If it's C, I'm doing this wrong. Okay, first one's A. Actually, I'm doing this somewhat wrong. First one could be any 4, right? A. That's right, because you can go AA. Repetition is allowed. Repetition's allowed, but they can't be consecutive. So if first one is A, the second one can be A, C, and D. If the second one is, say again, A, the third one can be, again, A, C, and D. And if the third one is A, it is again A, C, and D. So that would be again, so I would think it would be like this. I would think. Okay. I'm either going to be correct or way off. So We're going to find out in a minute. Okay. First one is 26 times 26. What is it? And the second one is correct. Hey, look at that. I'm on a roll today. Even though I am sick, I'm on a roll. Now, okay, check it out. This is the best part about it, right? I probably would not have gotten this correct if I hadn't made the toy model. And this is something that, is a very valuable tool, which I haven't really seen any math book, but I've personally used myself, is if the problem is difficult, but it's simple enough to where you can break it down to its essence and recreate it in a simplified version by reducing the number of variables, for example. I mean, as long as you keep the iterations the same, but reduce the number of variables, you could work with it and then figure out what's happening. Because if I had done all the alphabets, I could have gotten lost in all of them. Here, I'm just working with the 4 variables. I just ran through all the possibilities on the fly, right? That's a very useful tool that I use. I'm not a mathematician. I'm a landscaper / handyman / figure skating coach. But I am a university student at Westchester University in pure math and computer science. But anyway, I'm trying to say is that this is a very valuable tool if you utilize it yourself. At least it works for me. So, hey, maybe it'll work for you. Alrighty. Let's go to 9. A new car comes in a choice of 5 colors. So it's not a Ford Model T. 3 engine sizes and 2 transmissions. How many different combinations are there? Okay. So we have 5 colors, right? 3 engine sizes, and we have 2 transmissions, so automatic and manual. Okay, so then we're just going to multiply. Okay, 5 times 3 times 2. Okay, so that's 30. Okay, so then because we have 5 choices, 3 engine sizes, and 2 transmissions, 30. All right, let's take a look. All right. Yep. The answer's 30. That last one was simple. All right, we got through 3.2. How exciting was that? And we are still here. Wow, so cool. All right, well, join me next time for 3.3, where we're going to do more of this stuff. All right, I'll see you next time.